Hello all, in this tutorial we are going to learn about how to convert normal images to cartoon images using white box cartoonization method. So let's get started. So here we will be cartoonizing the images using machine learning. So I'll explain why we'll be using machine learning instead of doing it manually. So this paper called Learning to Cartoonize Using White Box Cartoon Representations by University of Tokyo and Style to Paints researchers called Wang and Yu. So what they did is like they introduced a framework that can generate high quality cartoonized images with much improved controllability in order to meet artist requirements. See, the ultimate goal of this paper is to meet the artist requirements exactly across wide range of styles and use cases. So why cartoonization is difficult? So and why we are using machine learning here? Because when we are cartoonizing the images manually, we'll be having a lot of difficulties, like we'll be facing a lot of them. Is like we need to have a task specific assumptions, or we also need to have a prior knowledge to develop any usable algorithms. And we also have other difficulties, like we need to pay more attention to global palette themes, and treat the sharpness of lines exactly. Or we also have the other difficulties, like we need to see sparse and clean color blocks, which will be playing a dominant role instead of uh, other colors, and with global palette themes relatively less emphasized. So here, so these are like all black box cartoonization models, where they struggle to effectively deal with such diverse workflow requirements, because we got many other models previously where they are trying to convert normal images to cartoon images. So most of them are like black box models. So what exactly black box is? Where we'll be knowing only the input and output. We don't know what exactly is going inside the algorithms. So that is what black box is, which where we'll be having less interpretability of the algorithm. So we don't know much what exactly going behind the algorithms. So okay, let's get back. So these black box cartoonization models struggle to effectively deal with such diverse workflow requirements. And using a black box model to directly fit the training data can negatively affect generality and stylization quality, which results in the poor quality outputs. So what authors did is like they created a white box cartoonization method, where the researchers closely worked with the artists, and they identified three separate representations, which mix up to uh, have an animation images. So the three representations are like surface representations, structure representations, and the texture representations. So what exactly these three are? So when we go into surface representations, which are like extraction of the smooth surface of image, and the color composition of surface texture are, are preserved with edges and textures. So that is what surface representation will be doing. And when we come to a structure representation, which effectively sees the global structure information, and also sparks color blocks in celluloid cartoon style. So this is what these two representations will be doing. And when we come to texture representations, it will be like all the complete painting details and the complete edges and everything. Or you can see it clearly here, like what the exact the surface representation will be doing, um, and the smooth surfaces, and and the structure representation and the texture representation here. So how exactly this algorithm, how exactly this model works, this white box cartoonization works? So after, see, we have three representations here, and we will be extracting the representations of the input images and the cartoon images, and then we will be using GANs here. Uh, do you know what exactly GAN is? I'll explain that. So these GAN consists of two networks, okay, and which is a generator and a discriminator. So they both work simultaneously to learn and train a model, and they both play an adversarial game here, where the generators always tries to fool the discriminator by generating data similar to those in the training set. Okay, and the discriminator tries not to be fooled by identifying fake data from real data. So this is what these two networks will be doing in the GANs, and the author used the GANs uh, to generate the animated images. So where these GANs are used to learn the extracted representations and cartoonize the input images. And here you can also control the output styles by adjusting the weight of each representation in the loss function. Okay, and now I'll explain the complete architecture in detail, like what exactly every module will be doing. So when we come to uh, see, if we can see, there are three image representations in the right side, where the structure representation and the texture representation here and the surface representation here, and we have one generator and two discriminators here. If you see, this is one generator and this is one discriminator and the other discriminator here, where d texture and d surface are the two discriminators, and we have one generator here, where the discriminator, like surface discriminator, what it will be doing, like it aims to distinguish between the surface representation extracted from model outputs and cartoons. Like it will try to um, find the similarity between these two images, the output image of the generator and the output image of the cartoon images, and it will try to map whether these two are true, whether the output from the generator is real or not. And the same thing the discriminator, texture discriminator, will be doing, where it tries to distinguish between the texture representation extracted from the outputs and the cartoons. Okay, and we also have one VGG16 model here. If you see these orange blocks, which is a pre-trained VGG16 model, which will be used to extract the high level features and to impose spatial constraint on global contents between extracted structure representations and outputs, and also between the input photos and the outputs. If you see, we are just directly passing the input images here and the output as well, and also the structure representation of the output images here. So we will be passing these three as an input, and then we will be um, finding the loss, like content loss and the structure loss, and from these two discriminators we'll be calculating the other two loss functions, texture loss and the surface loss. So where these loss functions will say how good the generator is doing. So if it is not doing good, the generator will learn to do good, like it will update its weights, and will be passing the same information to discriminator, and the discriminator will be saying whether the generator is doing good or not. And when we are doing so when we are doing, when we are learning from the structure representations, here we will be using adaptive coloring algorithm. So why we will be using that one is, it will effectively enhances the contrast of the images and reduce the hazing effect. So because of that, we will be using um, adaptive coloring algorithm in the structure representations, which helps us to extract more contrast colors. And this is what this is what the high level overview of the exact algorithm, what exactly happening behind. I'm not going in depth of the math behind this algorithm, so I just want to explain the high level and just go into the demo thing. Okay, And yes, this is the best model right now, because when a study is when they did a study like with 10 respondents and 30 images, the proposed approach outperformed three existing cartoonization methods, a cycle GAN. I don't remember the other two, but uh, they outperform these algorithm outperform those three algorithms in both cartoon quality and the overall quality as well. Like these are the three examples I did. Like these are the three images I converted. So if you see, this is the left side are the original images and the right side are the cartoon images. So if you see how good the algorithm is performing, like if you can give any dimension data and it will give the uh, HD quality of the art images. So this is how it works. And and what we will be learning in this tutorial. So I just explained the small theoretical concepts, like what exactly they are doing and how the algorithm is working. So I completed that part, and the next part what we'll be doing is like we'll be having a small demo, how we'll be converting the images to cartoon images by using the original implementation by the authors, and then we convert that original model into TensorFlow JS model, because we need to deploy that on the web. And then finally we'll be deploying this on the GitHub pages, where we don't need to have any server. We'll be just hosting that completely on GitHub. So, and you can directly interact with that model on the browser itself. Okay, then let's get started with the demo session. Okay, let's see the demo of this white box cartoonization. uh, so Mm, and yeah, we need to mention the credits completely. Like a big thanks to Wang and you for creating, such an amazing application, where you can find the original paper link here and the code for that one here. And we also need to thank Margaret and Sayak for creating the light version of this model, where they deployed it on Android, and most of the code is taken from them. The main code which I just taken from them is like converting the original model, which is written in TensorFlow 1, to a saved model, and then we will be converting that saved model to a TensorFlow JS model. And we also need to thank Pratap Vardhan. Like he did an amazing job where he created a web app of this TensorFlow JS, where I also just mentioned the link on my GitHub, so you can play the application which he created. Um, and that's all the credits I definitely need to give. So I'm okay. Let's get started here right now. So this is the original code version. So we'll be just cloning that complete repository into our Google Colab, and we also need to install these two libraries like TFSlim and the TensorFlow.js, where we'll be using that to convert the models, the main model into the TensorFlow.js model, and we'll be just importing few libraries. And this is what the main function. This is what the main code, the cartoonized code, which is written by the authors. You can find that code here. This is the repository we clone, and you can find that cartoonize here. This is the cartoonize.py file. So this is the main file which we'll be using to convert the images. So we'll be just creating an input folder to just upload the images here. So let me upload the images, which I'll be just uploading the same images which I used to create, which I shown you in the previous tutorial. So I'll be just uploading those images here, and if you check, we created the input folder, and we'll be having all the images here. And once it is done, okay, let it is still uploading the other two images. So once it is done, we'll be get back to the content folder, because we just gone into the input folder to upload the images, and we'll just get back to the content folder here. And this is the main code where we will be cartoonizing the images. So we need to have three things here, which is model path and the load folder and the saved folder. So this is where the model path, where we'll be giving the saved models. So what the authors has did is they created the checkpoints of the model. So if you check the repository here, um, you can find the saved models here, where you'll be having the model checkpoints. So we'll be using the same checkpoints to just infer the um, infer the model. So we'll be passing all the input images which we have in the input folder. So we have four images here which will be passing through the input folder, which will not take much time to just convert all the four images, which is very fast. And then if you want, we can just check how good the model performed in creating in just converting the normal images into cartoon images. So if you see how good it is, like it is converting the images into cartoon images. So if you want, we can see the other images as well. So let's see how Dhoni images converted into cartoon. So we can just change the names and we can see how good it converted. Like if you see uh, the face and the clothes here, how good it converted. And what I created here is like I also created a model where it will be converting the complete video uh, into the cartoon video. So I'm just creating two folders, input folder and the output folder. So here I'll be uploading the video here. So okay, this is the file I just uploaded. uh, so let me show you the video, what exactly the video content consists of. So okay, I'm just showing how what is the video I'm just going
I
to
was
show.
13 when I
This is the video
first got
which will be
access
converted
to
into cartoon
a computer.
video.
My
So we
parents
have
bought me
the
a
tag
Macintosh
Program
before when I was 8 years
and we
old.
also
I was in
have
6th grade.
I learned to code in college.
Freshman year, first semester, intro to computer science.
I wrote a program to play tic-tac-toe.
I think it was pretty humble beginnings. I think the first program I wrote asked things like, what's your favorite color? Or how old are you?
I first learned how to make a green circle and a red square appear on the screen.
The first time I actually had something come up and say, hello world, and I made a computer do that. It was just
where
astonishing.
we'll be passing the path of the video and we'll be capturing every frame here, and we'll be writing that every frame into video input. We'll be just taking the video and converting that video into number of frames. Like it will be just converting that into frames. Frame is nothing but a different image. So we are just converting it into the images. So this is the path, video path. So if you see the video input, the frames will be generating here. And yes, it completed that one. So we'll be just going into back to the content folder. So here what we will be doing, like we'll be passing all those frames through the cartoonized model. So it will be taking all the 920 frames of this image, of this video, 920 frames, and it will be converting all those 920 frames into cartoon frames. So if we see video input, let me go to the video folder. So it will be generating all the images continuously, the cartoon images. So it is going to take a bit of time. So I'll just get back after it is done. Oh yes, it is done. Like it converted all the 920 frames into cartoon frames. So we'll be using this code part to combine all those frames into a video again. So here if you see, we'll be using 25 frames per second, and we'll be uh, combining all those frames into one single video. It will not take much time, like it will be converting very fast, like it will be taking all the frames and it will be converting that into a video. And but what one disadvantage of this one is, like, we'll be losing the audio, we'll be just having only the video here. So the video is it is converted like we got the video out. So let me just download that one and play that for you, so you can see how good the model performed in converting the normally video into a cartoon video. Okay, we downloaded the video. Let me play that one, so you can see how good it converted the complete video into a cartoon video. So if you see, you can imagine how good it is. Okay, I think we completed that one, so let's get back to the code. And the next thing what we will be doing is, um yes, and the next thing what we'll be doing is, like, we'll be creating the saved model version of this uh, original code by the authors, because the original white box cartoon GAN model is implemented in TensorFlow 1. So we first need to generate a single self-contained model file in a saved model format using a TensorFlow 1.15 version. Then we'll switch back to the TensorFlow 2 and we'll be converting that saved model format into the TensorFlow JS format. So we'll be just first creating a folder to save all the models, and we'll be importing two files, network and guided filter, which you can see all of them in the test code itself, where we'll be having the network.py and guided filter.py here. So we'll be switching to TensorFlow 1, and then the one thing what we the steps will be doing the steps we'll be following here is, the first step will be creating a placeholder for the model input, and then we instantiate the model instance and run the input placeholder through the model to get a placeholder for the model output, and then we load the pre-trained checkpoints into the current session of the model, and then finally we export that into a saved model format. So if you see, we'll be having a placeholder here, and we'll be running the input placeholder through the generator and then apply the filter, and then we'll be converting that into a saved model format here. So it is done. So if you can check, like you can check here, like we'll be having the pb file and the variable file, which is the standard saved model format in TensorFlow, and then here we'll be converting that into the TensorFlow JS format. So here we'll be just normally converting that into a TensorFlow JS with a default quantization. So what exactly quantization is? Quantization is nothing but it is a step to optimize more of your model. Normally the weights and activations will be in float 32. So when we use quantizations, we'll be converting that into float 16 or integer with 8 bits precision. So we'll be doing that one. So default will be like, it will be converting the weights into unit 8, and sorry, the weights into 8-bit precision, and the activations will be in the same format, but the activations values will be the dynamic, like when we it will be stored in float 32, but when we are processing, that float 32 values will be converted to um, 8-bit precision, and after the processing it will be converted back to float 32. So that is one quantization method, which is default, and here we'll be quantizing the weights into float 16. Normally we use float 16 when we have GPUs, because GPUs works directly with the float 16. But if you convert this into float 16, and when we have CPU, what it will be doing is, it will be converting that float 16 into float 32 before processing, and it will process all the output and input, and then it will be converted back to float 16 values. So that is what float 16 quantization will be doing. And we also have the other one is like unit 8. Unit 8 quantization is the fastest one, because it will be, all the weights will be converted into the integers, the float values into the integers. So it is the fastest, like the processing speed will be very fast here. So we just converted that saved model into three different formats, which will be having a default quantization and the float 16 quantization, and we also have unit 8 quantization. So this is how we'll be converting the saved model into TensorFlow JS. And if you check, we have three models here: the web float 16, and web int 8. And you can also see the memory of these three saved files. Where if you see web, it is around 5.7 MB, and web float 16 is 2.9 MB, and the web uint 8 is very small, like 3x or 4x smaller, 1.5 MB. Because of that only it is more faster. And you can download all these models into your local, where first we need to zip all these models, and you can just directly download all those models in a zip format into your local system, where we'll be creating the a web application by using all these models here. So this is the exact code of our web application, where we'll be having two files. One is HTML and the other one is JavaScript file. And we also have these three models which we just created, which we just converted from saved model to TensorFlow JS models. So if you see the web application, it is very simple, minimal design, where we will be just uploading the image here. So let's just upload some image here, and we just wait for 10 to 15 seconds. So it will be generating the cartoonized image here. So it is taking a bit of time because we'll be having a high resolution image. So if you want low resolution images, you can also do that one, where you'll be getting the output very faster, instead of waiting for more time. But if you want the HD images, you need to wait for some good amount of time. So it will be converting this image into the uh, HD format cartoon image, and let it convert. But if you see, this is a small HTML file, like this is self-explanatory, like I don't need to explain anything. But three things which we need to do is, like, we need to include these three scripts. One is the TensorFlow JS library, and the other one is TensorFlow backend library, and we also need to include the model.js file which we written. And this complete code is taken from Pratap, uh, as I explained before, as in the credits. So this is what he created is, like, he created a app uh, where we'll be having all the element IDs, and this is what the important for us, like the path of the model we need to use, and the size of the image. So if you reduce this size, the time will be reduced in converting the normal image into cartoon image. And if you increase this size, the time also increases and the computation cost also increases. So if you have more resources with GPU, then you can increase the size. But if you don't have anything, then reduce the size, which is better. And this is the function run model, where the model will be loaded, and it will be predicting the output image. So this is where we'll be loading the model, where we'll be just giving the path, and we'll be having a load graph model function, which will be loading the saved format model. If you converted the Keras model into TensorFlow JS, you'll be having a different function here. Because we converted saved model into TensorFlow JS, we'll be using this function to load the JS model. And then here we'll be having onload and session timeout, so where we'll be uh, giving the output image in this block. So if you say this is what the converted image with the high resolution HD images, and here we'll be predicting that one. So if we go into the predict function, where we'll be taking the input image from the image element, we'll be using tf.browser.from pixels, where we'll be taking the images into a tensors. We'll be converting that image pixels into a tensor values, and we'll be normalizing the image. Without normalizing, we cannot get the exact output. So we need to normalize the image, where we'll be padding few values if the height and width is not exactly matched, and then we'll be having the size here, which we have given 1000. So we'll be resizing that one using resize bilinear, and then we'll be reshaping that into the format which uh, TensorFlow expect to have. So we'll be resizing that image into the format, and we'll be predicting that image from this function like model.predict, and we'll be passing the image here. So it will generate the output, and we'll be just doing some squeezing that output into the format exactly how the image will be. So we'll be doing all those things, and we'll be just giving out that image into the canvas function, so where it will be displaying the image here. So this is how exactly the TensorFlow JS model works on browser. So we don't need any server here, we just need the model file, the JSON file, and some web application like this to pass the information to that JSON file. So all the information, all the images which you uploaded here will be on your browser itself. It will not go in anywhere, because it will be running on your browser only. So and then when you just create a repository for all these things, like you create a new repository and upload all these files exactly there. And so I'll just show how I deployed using Google Pages, sorry, GitHub Pages. So let me go to the repositories, and this is what the white box cartoonization, the exact code for this one. So I just uploaded all the files which I just shown you in the editor. So we'll be having all the same files, and we need to have an index.html. If you don't have a website linked to your GitHub, uh, a website is already linked to my GitHub, so I'm using the index.md files here, markdown files. So when you just go to the settings, and you'll be having an option here, the GitHub Pages, where you just select the branch and the select the folder, and when you just click the save button, you'll be getting a website link here with your username, like username.github.io, and the project folder name here. Because I already linked the website here, so I'm getting the project folder which is linked to my website. So when I just click this link, so we'll be having the same UI which we have from the local, where we will be uploading the image, and you can convert that into a cartoon image here. And that's it from this tutorial. Like if you want to learn more, I'll just mention more resources about the white box cartoonization in the description, and you can also find the code link there, where you can uh, just fork the repository and play with that one. And that's it from this tutorial, guys. So thank you so much for watching.